Hi, my name is Florian Przybylak, and this project was created as part of IBM's online course to become a data scientist. Have fun with binary classification of injection molding data. The goal of the project was to analyze a data set using machine learning and statistical methods. I decided to classify injection molding machine data in a binary way. In this presentation, I will explain my approach and my interpretation of the results. If you have any ideas or suggestions about the project, please comment. At the end of the video, I will also include my email address. Feel free to write me directly as well. I look forward to your comments. Okay. So here we go. First of all, I want to show you the motivation behind binary classification using today's approach to quality control of injection molded parts. Since I used a company internal data set, I would like to explain the experimental setup and procedure in the next step. In the second section, I will show you the first exploration of the data set, which of the data sets, which initial findings I was able to make here, and which consequential decisions I had to make for the further analysis steps. The third section is about the actual data analysis, which I then interpret in the last section again, and a look into the future. Now we come to the actual goal of this experiment. This is closely related to the current quality testing standards in the injection molding industry. So what is the current standard and what opportunities do AI solutions offer? Up to now, two testing methods have been established to a large extent. One is the sample quality test, in which a workpiece is randomly tested for various properties. This is done, for example, by weighing and optical surface inspection by trained personnel. However, this inspection is time-consuming and usually involves a high level of disposal of batch concerned. Optical inspections, which are carried out subsequently, can rarely be assigned to a specific workpiece. Here too, the reject rate is high. Further quality control can be achieved by checking some machine parameters. Here, specific guideline value violates are observed. However, this test method cannot completely replace an optical inspection. Not every quality influencing factor is called up by sensors, and the relationships between data and workpiece are usually highly dimensional. With the help of artificially intelligent methods, it is possible to analyze high-dimensional data sets in real time. Once trained, machine learning processes can calculate causal relationships between machine data and the quality of a workpiece within milliseconds. Workpieces affected in this way should then be immediately sorted out fully automatically, and the volume of waste kept as low as possible. The application on a production line poses a number of difficulties. Various recipes can be run within one day. An artificial intelligence must therefore be trained during production on the basis of data streams. This experiment should be the first step towards a production assistance AI and map the data situation within various experiments. So what did the experimental setup look like? An injection molding machine was used to produce comps for a few hours. The machine data was accessed both via an UPC UA server, via which the PLC controller published the data, and via a specific interface from the machine manufacturer. UPC UA is an industry standard data protocol. The data is provided in a tree-like structure within own namespaces via nodes. As soon as the values change, they are published. The manufacturer's own interface is capable of publishing data packets in binary form at 10 milliseconds intervals. To handle the high volume of data, They were first written to a Kafka message broker and synchronized there. Since the injection molding process runs cyclically, the data can be arranged logically in this way. However, the machine timestamp is only published via UPC UA and must be added to the other data via event bits exactly, a circumstance that will still affect the course of the experiment. This data is forwarded to an AI partner company. For this purpose, a Kafka in the Azure Cloud, Microsoft's cloud computing platform, serves as the enterprise interface. Since the Kafka parallelism makes it suitable for processing large volumes of data, but it is not yet used as standard for unlimited data persistence. I consumed it again and stored it locally in the timescaledb time series database. This database is based on PostgreSQL and is characterized by its time-based partitioning in addition to its performance with JSON objects. This divides the data into logical groups vertically and horizontally based on time. This allows query to be performed incredibly fast. Here I did the first pre-processing in SQL and converted the data into a JSON format. So, what did the testing process look like? First of all, it was important to produce as broad a spectrum of machine data as possible. In the first instance, idle data was created for a few hours, and then temperatures were changed during production. The most exciting question was whether it is possible to draw conclusions about the other parameters based on temperature changes that are not tapped directly. Without anticipating too much, here is a look at two temperature sensor values taken at different points of the machine. Here in the left picture, you can see this change extremely in the temperature data of the feeding zone. As already mentioned, data is only received when the value changes. So the values in the heating phase describe a relative coherent curve, while later the temperature is kept more and more stable. This sensor was the most affected by the manipulations. On the right, you can see the values recorded at the same time in heating zone 1. Here, the own temperature course is already influenced, not so extremely, and also somewhat time delayed. Both curves only contain values from the UPC-UA interface. I will now explain why this is the case. So what does the dataset look like and how did I adjust my pre-processing? This step is now handled quickly by me, but was very time-consuming in relation. Especially working with several million data entries was challenging. However, the choice of technology was particularly decisive here. Through the pre-processing steps, which I wrote in pure SQL, I was able to perform very high performance queries and save a lot of time. When I first looked at the dataset, I unfortunately found that the data from the two interfaces were not synchronized correctly. Here on the left, you can see that per cycle the data volume diverges extremely. In the right figure, it is clear that at different times different cycles were assigned. Since a certain regularity became apparent, I tried to correct the data afterwards. However, this did not work at first go. In order not to blow up the framework of this experiment unnecessarily, I decided to do without the data from the high-frequency interface for the first time being. So, a few million data points became a few thousand. To summarize all steps of the pre-processing, I first consumed the data from the Kafka and sorted it into a DB schema. In the next step, I removed all data points from the interface from the machine manufacturer. I removed all nulls from the dataset, as they cannot be interpreted by analysis algorithm. Finally, I labeled the data by timestamp. I will explain how in detail. All other operations I handled via pandas, a Python library own data type data frame. This data type is similar to an SQL schema and is optimized for large data sets. Many algorithms can be fed directly with this data type. Since pandas also builds on NumPy and its tensors, data frames can be easily converted to NumPy arrays. Tensors are multidimensional matrices and form the basis for learning with neural networks. So far, the dataset is prepared for the first analysis. But before we continue here, first a few terms that I will mention so casually and already have. This section is especially for my colleagues who might have a look at this. If you want to jump directly to the analysis, please click on the info. First things first. You've probably heard the terms AI, machine learning, deep learning. Otherwise, you probably wouldn't have found this video. But do you really know what the terms stand for? It's important that you understand that the terms are mutually inclusive. When you talk about AI, you automatically talk about machine and deep learning. AI describes the science itself, how you write intelligent programs that can solve problems creatively. Machine learning is a field of AI science. It is primarily about how systems are given the ability to learn automatically from experience. For this purpose, algorithms such as deep learning methods are used. If you want to know more about this topic, check out the article in the description. The learning behavior of machine learning algorithms can be roughly divided into three main categories. In my experiment, I only used methods from the first two categories. I therefore omit reinforcement training. In supervised learning, an algorithm iteratively learns the dependency between data points. The output to be learned is determined in advance, and the learning process is monitored by matching predictions. Supervised learning methods can be applied to both regression, it means prediction or trend prediction, and classification problems. In unsupervised learning, patterns are determined in data without initial patterns and relationships being known. Especially in complex tasks, these methods can be useful to find solutions that would hardly be solvable by hand. In unsupervised machine learning methods, two basic principles, which also classify the algorithms used, can be distinguished: the clustering and the dimensional reduction. Okay, so much to the terminology. But before we can start with the machine learning methods, feature engineering has to be done first. That is, roughly speaking, the preparation of data for the processing in machine learning algorithms. If possible, the raw data is prepared in such a way that only data that is important for the training is taken. I decided to do a two-part experiment based on the data. First of all, I wanted to know how the production data differ from the idle data. What features are interesting, and can machine learning methods distinguish the two cases? In the second step, I wanted to compare this production with an older production dataset. In this dataset, other machinal parameters were manipulated during production. What are the features here, and can an artificial intelligence make a distinction? Here I was hoping for extreme differences in the datasets that an AI could potentially pick out. So first a question: are there differences in the data between idle and production, and which parameters are primarily affected? For first orientation, I created a heat map over all sensors. A heat map is simply a data representation where the values have been replaced by a color index. This allows you to quickly identify areas that are important even in large data sets. This is a correlation matrix. Here each square shows the correlation between the variables on each axis. This ranges from -1 to 1. A value around null means there's no linear trend to be seen there. 1 indicates a positive correlation, -1 a negative correlation. With a positive correlation, if one variable increases, the other also increases. With a negative correlation, it is the other way around. The stronger one variable increases, the stronger the other variable decreases. It becomes obvious that the sensors, which are divided into logical groups of the UPCUA tree structure, show strong positive correlations within the groups. For example, in the temperatures here and here. Here I have taken the average sensor amplitudes of both datasets and normalized them. On the x-axis, you can see the index of the sensor array. Blue here is the idle data and 1 is the production data. If sensor data is missing from the production run but appears during the idle phase, as for example at index 125, this does not mean that the value has fallen to 0, but that it has not changed during the test and therefore no new values were received for this sensor. In this figure you can see nicely around 200 the deviations of both data sets in the actual temperatures. In the next step, I wanted to evaluate the importance of each feature in a binary classification. For this, I calculated the feature importance score with extreme gradient boosted trees, short XGBoost. The library provides different methods. However, I used the number of times a feature is used to split the data across all trees. Here, the actual shot volume is identified as the most important feature used to distinguish the two data sets most often in the binary classification. In second place, the actual cycle counter is used as a feature, a value that does not change during an idle cycle, but counts up during production. From this point of view, an important feature. One possibility would be to remove this feature, to put the focus on other features during training. I did not remove this feature, however, because primarily exploring learning performance on raw data was more important to me here than an optimized model. After the actual switching time reprint, the first temperature sensors are also assigned a high importance. Before I ventured the first training, I wanted to look at the most important feature in detail. No wonder that this feature was rated very high. When idling, there is no variance in shot volume because there's no production. Similarly, for the mass quotient and injection time, at idle, these do not occur, but are still rated lower than some temperatures. So much for the differences between the production and idle data. In the next step, I took an older test run, pre-processed it in the same way and compared it with the new production run. The correlation matrix immediately shows a different picture. Almost across all sensors, there are strong to strongly positive correlations. The amplitudes of the individual sensors now also give a more consistent picture. The 0 in this case is the old test dataset, and the one unchanged is that of the current test. So during production, certain sensors can be observed more appropriately. The large difference in the closing force is due to the fact that it was extremely manipulated in the first experiment. Here too, a large difference can be found between the temperature sensors, but a difference can also be seen in the shot volume. In the recalculation of the feature weights, the cushion, the actual shot volume, and other values related to the amount of material used are rated highly by a large margin. It can therefore be assumed that changes in other production parameters, which are not directly mapped via a sensor, can possibly be indirectly inferred via the injected material volume. To compare the two feature extraction methods, since the results differ, it should be noted at this point that the largest differences do not determine the evaluation of the features. Also, both negative and positive differences are interpreted equally. Here, it is primarily the distribution across the data sets that is important. And if we look at the main feature, caution, in a direct comparison between the two data sets, we can see different distributions. In the second experiment, the data distributions are clearly more stable than in the first. Over this representation, the different distributions become also again beautifully clear. The range of values in the first experiment is clearly subject to greater fluctuations than in the second experiment. Here it is the representation not in dependence to the quality, but in dependence to the attempt. The major of all cushions here are in the range 0 to 0.5, while the old data set is primarily divided into the ranges 0 to 1 and 1.5 to 2. The difference between the two tests can also be seen in the injection times. Although the mass cushion is much larger in the old one, the injection times are much shorter. So much for the consideration of the features. The next step, the different data sets should be classified binary by deep neural networks. For this, I had to divide the data into training and validation data sets randomly. First of all, a conceptualization. What is a perceptron? A perceptron is a simple binary classification algorithm modeled after the biological neuron, and thus a very simple learning machine. Here, the output function is determined by the weighting of the inputs and by the thresholds. Perceptrons are used for both machine learning and artificial intelligence applications. By training with certain input patterns, similar patterns can thus be found in a dataset to be analyzed. The figure on the right shows schematically the learning process. If the weighting of the inputs exceeds or falls below a specified threshold, the state of the neuron output changes. Thus, the perceptron has the ability to learn and solve complex problems by adjusting the weights. I primarily tried using such a perceptron to classify the datasets of both trials. However, the training was less successful. Compared to the validation dataset for the perceptron, the training dataset does not provide enough clear information to learn the problem. More data would be needed here. For example, both datasets are not clearly linearly separable. Thus, no valid result can be obtained. Obviously, with this data, the network topology has to be adapted to improve the training in a sustainable way. A multi-layer perceptron corresponds to a so-called neural network. Perceptrons, thus, form the neural bases, which are interconnected in different layers. The perceptron uses different weights for each signal, and the output of a neuron is the input vector of a neuron in the next layer. The variety of classification possibilities increases with the number of layers. In feed-forward networks, the outputs are connected only to the inputs of a subsequent layer. They may be fully connected, in which case the neurons of one layer are connected to all the neurons of the layer immediately following. I tried several network topologies, but had the best results with the combination of low number dense layers and built-in dropout, as well as batch normalizations. Thus, I could stabilize the training to some extent, but had to accept that patterns in the validation data sets could be found correspondingly easier. At first, I wanted to do the binary classification between the idle and production. The network also quickly reached the lowest error with a high accuracy. In the further training process, the training loss stabilized. Since the large batch size here caused a relatively large generalization gap between the two errors, I reduced the learning rate to 0.0001 to counteract this. However, the network was overall very good at classifying the datasets with a high accuracy and a low loss. Distinguishing between the two experimental productions, on the other hand, seemed more difficult given the volume of data. Training was correspondingly much more choppy. However, it was still possible to classify with a good error accuracy ratio. At the end, I tested the performance of further machine learning classification algorithms. Accuracy and precision are to be understood in context. Here in the right picture, all possible combinations are visualized. In the optimal case, both values are very high on the same extent. These are the results of the runs of the individual machine learning algorithms. Basically, it can be summarized that almost all methods perform worse than my network. Also, the poor performance of the logistic regression supports the thesis of the poor performance of the perceptron, that the datasets are not clearly linearly separable. Only the random forest decision tree algorithm, in which the tree is built up step by step in a learning process similar to the neural network, according to the importance of the input features in the context of the specific application. This algorithm shows its strengths in the case of missing data, because not every tree uses the same features. Thus, there are always enough trees that manage without this feature. However, this algorithm is limited in that random forests perform poorly on data that is outside the range of the original training data. The question of which algorithm is better suited for predict the quality of work pieces will be addressed by further experimentation. However, a neural network is primarily more robust against high data noise and many outliers. So, how do I evaluate the experiment? In conclusion, it remains to be summarized. Differences can be found in the parameters between idle and production, as well as between two different production processes. A deep neural network is able to assign the individual products to the production processes. So, what do I think should be done? A further test between the production processes of a good or bad production would be interesting in the next step. For this purpose, a larger dataset should be produced to stabilize the training and to avoid overfitting. By integrating the other higher frequency interface, a more complete view of the parameters can be ensured and further features can be added to the production processes. I'm looking forward to further experiments and results. I would like to conclude this somewhat more detailed presentation with a quote from W. Edwards Deming: "Without data, you're just another person with an opinion." Okay, thanks. I hope you could take something for yourselves. Please comment diligently or contact me directly. Thank you for your attention. See you then.